Hey guys, welcome to the first installment for Chapter 16 lecture. And Chapter 16 is all about acids and bases. Now, I also should tell you that some of this material was actually introduced in Chapter 8. I did not introduce it in class last semester when we did Chapter 8. Chapter 8 already sort of had enough stuff in it. But you may want to flip back to Chapter 8, the section on acids and bases, for a little bit of some of this introductory information. But I'm going to go through it in this lecture, so hopefully it's clear to you. So, acids and bases. Acids and bases. Alright, acids and bases have different properties. You can describe some of their different physical properties, but we'll spend a lot more time talking about different chemical properties. So, some of the things that are characteristic of acids are they tend to be sour tasting. So think of acidic foods, citruses, citric acid gives you that sour feeling. Acids can also dissolve. Aluminum foil, you shouldn't use it to cover acidic foods because it will actually dissolve the aluminum foil. I've learned that lesson myself when using it to cover up, I think it was a meatloaf with like a tomato, like a ketchup sauce on top. And when I came back the next day, there were all these little holes in the covering of the aluminum foil. And I was like, oh yeah, that's right. Ketchup is acidic. And then acids also can change. There's several different chemicals, like pigments, that will actually change color depending on the pH, whether something is acidic or basic. And the first widely used pH indicator is the plant pigment called litmus. And litmus paper turns red, when you touch it to an acid. So some examples of acids we use in chemistry: hydrochloric acid, so it's found in your stomach acid. Acetic acid, which is just vinegar, and the titration lab that you guys are going to be doing involves vinegar, acetic acid. Carbonic acid you find in carbonated beverages. When you dissolve carbon dioxide in water, it reacts with water to form carbonic acid, and that's why carbonated beverages are all a bit acidic. Bases tend to have different properties. They tend to be bitter tasting. There's not a lot of basic foods because they're not very tasty. A lot of poisons, like in plants, are actually bitter tasting. I guess the bitter taste was an adaptive evolutionary feature so that we wouldn't eat things that contain poison. Bases also tend to be slippery. Soaps and detergents are usually basic. They're actually made using a base and some kind of fat. And also, if you've ever used Drano to clear your drain, that's basically straight sodium hydroxide, which is a strong base. It's caustic and corrosive, so it dissolves things, but it's also slippery and helps it slide down your drain. And it turns that ever so famous pH indicator litmus blue. So those are some of the features or physical features of acids and bases. Now, what are the chemical definitions of acids and bases? Okay, so there's actually 3 different definitions in chemistry of acids and bases. The most basic or elementary one, and the first one, was by a scientist named Arrhenius, who's, I think, most famous for his work with acids and bases, but you may remember him from our chapter on kinetics. The Arrhenius equation was the one to calculate K using the frequency factor and the activation energy. All right, so Arrhenius said he defined acids as things that produce hydrogen ions in water. Hydrogen ions can also be called protons, because if you think about what a hydrogen atom is, it's just a proton and an electron, and when it becomes an ion, it loses that electron, and all that's left is the proton. So a hydrogen ion is just a proton. So hydrogen ion, H+, protons, all the same thing in chemistry. So how we could write this as an equation, we say, so technically hydrogen ions in water won't stay as free hydrogen ions in water. So when you add hydrogen ions to water, they will actually combine with the water molecules to form H3O+, which we call the hydronium ion. And that's a vocabulary term you should know. When I say hydronium ion, or if you see hydronium ion written, you should know it means H3O+. So in acid-base chemistry, protons, H+, are equivalent to hydronium ions, H3O+. This is what's being produced, but this is what actually exists in water. So you'll see them written sort of interchangeably. Now bases produce hydroxide ions. Hydroxide are OH- ions when they go into water. And that was Arrhenius's definitions. Basically, his definitions were based on adding things to water. And acids produce H+, and bases produce OH-. And it's not that he was wrong, it's just that his definition was somewhat limited. So later, along came two guys named Bronsted and Lowry. So the Bronsted-Lowry definition of acids and bases are that acids are proton donors and bases are proton acceptors. So what do they mean by that? So an acid, HA, some generic acid, A is just a generic placeholder element, gives up an electron, a proton, an H+. All right, so it sort of looks kind of like what Arrhenius said. It produces a proton. And a base is one that accepts a proton. So a base gets a hydrogen added to it. So let's look at some examples here. We've got HCl, hydrochloric acid, plus water reacts to form hydronium and chloride ion. So if we look at these molecules here, I've tried to sort of cartoon them out. So we've got HCl, it's a hydrogen and a chlorine, and H2O, which is an oxygen with two hydrogens on it. And then if we look at what happens in the course of the reaction, that H2O gains another hydrogen, and that chlorine lost its hydrogen. So since HCl lost its hydrogen, it is the acid. It basically donated this hydrogen to the water. So the HCl is the donor and the H2O is the acceptor. The donor is the acid, the acceptor is the base. And let's look at the second example. We've got NH3 ammonium and water reacts to form ammonium ion and hydroxide ion. So we can look at the molecules drawn underneath them. So NH3, on the other side of the equation, it becomes NH4. What happened? It gained a hydrogen. So basically it took one of those hydrogens from that water molecule, and the water molecule went from have an oxygen with two hydrogens to an oxygen with one hydrogen. So in this case, this one was the acid, the donor, and this one was the base. All right. So notice that that water here can act as be either a base or an acid. We do have molecules like this. I'm going to skip to the next page. All right, so water can act as an acid or a base. We call things like that amphoteric. All right, amphi, like an amphibian, can do both. Can live in both land and water. So amphi, I think it means both, or something close to that, okay? So an amphoteric substance can act as both an acid or a base. And water is a good example of something. So you can't always just memorize whether something is an acid or a base, because some things are amphoteric. So you really have to be able to look at the equation and see, did that substance lose a proton, donate a proton, or did it gain, accept a proton, and then identify it as an acid or a base. So we'll do some more practice problems with that. We're also going to talk a little bit about since a lot of chemical reactions are reversible, that means that the product can sort of react as the acid. It now has the hydrogen. Donate. So B and BH are also a conjugate acid-base pair. All right, so you might have questions in the homework that are presented like this, where it gives you two different chemical formulas, and it says, are they a conjugate base pair? Conjugate acid-base pair. And they are, basically, if they're exactly the same, except for the difference is a single hydrogen atom. And then they also might give you problems with an equation and ask you to identify, maybe like a sorting problem, which is the acid, which is the base, which is the conjugate acid and the conjugate base. So here's an example problem. Maybe pause the video here and try this. And I will work it right now. Okay, so I'm looking at the reactant side, and I want to identify first the acid and the base. So NH3, look at the other side of the equation, it becomes NH4. It accepted a hydrogen, it gained a hydrogen, so that means it is a base, a proton acceptor. I've been doing base in blue, so I'll stick with that. And that means that NH4 is the conjugate acid. And that also means that by default, if NH3 is the base, then water must be the acid, but I'll double check that. H2O becomes OH minus. It did indeed donate a proton. So that would make the OH minus the conjugate base. Okay, so another way to write this is that NH3 and NH4 ion are the base and the conjugate acid, and H2O and OH minus are the acid and the conjugate base. And we call these things conjugate acid-base pairs. All right, so here's a problem. Identify the Bronsted-Lowry acid, conjugate. I recommend you pause the video here, try it yourself, and then start it back up again. I'm just going to write out the answers. That should be a 3. This is the acid. Conjugate base. All right, so some trends that you also can start noticing. All right, if water is in the equation, and it is in all 4 of these, all right, if you see H3O plus on the other side, then you know water acted as a base. And if you see OH minus on the reactant side, you know that water acted as an acid. That's a pattern maybe you just learned. But some other things here. So what is tricky about all these, sometimes you can eyeball. And so for one thing, all acids have to have a hydrogen. Bronsted-Lowry acids have to have a hydrogen because by definition they donate a hydrogen. And so if you have a substance that doesn't have any hydrogens, well then you know they can't possibly act as an acid. But in all of these problems, both of the molecules had a hydrogen, so you couldn't just pick it based on that. You had to look at the reaction. H2SO4 becomes All right. Now we're going to talk about some different types of acids and acid strength before we go back to chemical equations. So acids, most acids that we will talk about, most of them, are binary acids. We'll go with maybe. Binary means it's made of two things. So examples are hydrofluoric acid, or hydrobromic acid, or hydrochloric acid, HCl. Right? We see those a lot. We'll also see a lot of oxy acids. All right, oxy means oxygen, so these are just acids that contain oxygen. Examples, nitric acid, HNO3, perchloric acid, HClO, sulfuric acid. There's also acids that are what we call polyprotic. Which really just means they have many protons. All right, poly means many. Proto for proton. All right, and remember a proton is an H+, so hydrogens. So these are just acids that contain multiple hydrogens. So we have diprotic acids, which have two hydrogens. An example is H2SO4, which is sulfuric acid. Triprotic acids, which have three hydrogens, and phosphoric acid, H3PO4, is an example of that. And the thing to know about polyprotic acids that we'll see that will become more relevant later on is that they lose their protons one at a time. So for example, sulfuric acid, H2SO4. All right, when you put it in water, it will dissociate into HSO4 minus and H plus, and then some of that HSO4, some of that HSO4 minus will dissociate into SO4 2 minus, the sulfate ion, and hydrogen ions. Okay, so it's a two-step process. 1, 2. It's not that it dissociates and forms two hydrogens at once. It does it one at a time, which is not what we usually see with like ionic substances, like for example, MgCl2. Right? It doesn't lose one chlorine at a time. It dissociates into Mg and two Cl minus ions. Okay, so this, with polyprotic acids, it's sort of a different situation. They're not ionic compounds. They are still covalent compounds, so they don't just fully dissociate, they tend to dissociate in stepwise fashion. All right, this first step I'll tell you because sulfuric acid is a very strong acid. This one happens almost to completion. Pretty much all of that H2SO4 will dissociate, but this second step is definitely not a one-way reaction. It's an equilibrium reaction. And as we saw in the last chapter, with equilibrium reactions, they do not go to completion. There's some amount of product and some amount of reactant. Okay, so that brings us to acid strength. So you've probably heard of strong acids and weak acids. And we know that acids can be corrosive and damaging. So obviously a strong acid is going to be more corrosive and damaging than a weak acid, but why that is has to do with the chemistry. So if you recall at all from last semester when we talked about electrolytes, which was also in chapter 8, all right, electrolytes are things that dissociate in water and form ions. And if they completely dissociate, we call them strong electrolytes. And acids are electrolytes. They do dissociate into charged particles. And so they are both a strong electrolyte, but since they're an acid, we call them a strong acid. So hydrochloric acid is a great example. HCl fully dissociates into hydrogen ions and chloride ions. Now, strong acids are in the minority of acids. There's only 6 strong acids. They are the halogens, hydrochloric, hydroiodic, and hydrobromic acid. And then nitric acid, sulfuric acid, and perchloric acid. Those are the 6 strong acids. You don't have to memorize them. I will give you those on a key, on your test key, so you can reference that. All the other acids, though, on Earth are classified as weak acids. And weak acids, just as weak electrolytes, only partially dissociate when you put them in solution. So, for example, hydrofluoric acid, although fluoride is a halogen with chlorine, iodine, and bromine, it's not a strong acid, it's a weak acid. And it only partially dissociates, so it has an equilibrium arrow as opposed to a one-way arrow that strong acids have. And most acids do fall in this category. So, weak acids are not all created equally. There are features of the chemistry or physics, I suppose, that influence whether an acid is a strong acid or a weak acid. So some of the things that determine acid strength, the first one is bond polarity. All right, so HLI, I don't even know what that would be called, hydrogen lithiamide? I don't even know. I'd have to look that up. But this bond is not acidic because hydrogen and lithium both have very low electromagnetic differences. But hydrogen's actually a little bit stronger than lithium because lithium is a metal and hydrogen is a non-metal. If we look these up, I think hydrogen is 2.1 and lithium would be 1 point something. Let's say 1.5. All right. So in this case, hydrogen is the hog. And in a rare occurrence, hydrogen is actually partially negative in this molecule. It's hogging the electrons. All right, so that hydrogen's not going to go anywhere. H and C, hydrogen and carbon bonds, are nonpolar. So there's no chance really that this is a pretty strong bond because there's a lot of even sharing. So that hydrogen doesn't want to leave the carbon. And the carbon doesn't want to take electrons from the hydrogen. All right, when you have a polar hydrogen bond where you have something more electronegative bonded to that hydrogen, it pulls on the electrons, which makes it pretty easy for that proton to escape because that fluorine's already stealing or really hogging those electrons, and in a split second, it could take those electrons and the hydrogen could just skedaddle out of there, okay? So if you have a polar bond where that hydrogen is partially positive, then that's going to lead to a more acidic molecule, all right? Same thing here. We've got hydrogen's 3 different oxyacids where hydrogen is bonded to oxygen in each of these. All right, so iodine, bromine, and chlorine on the periodic table look like this. And here's fluorine up here. So remember, fluorine is the most electronegative, and it gets more electronegative as we go up. So chlorine is the next most electronegative, then bromine, then iodine. So it makes sense that this molecule would have the largest dipole moment, the largest pull of electrons away from that hydrogen. All right, so all of these do pull electrons away from that hydrogen, but if we were to sort of classify these, all of these are acidic, but this one is the most acidic, this one's sort of middle acidic, and this one's the weakest acid of the 3. And that's because that hydrogen is the least polarized of those 3 molecules. Another thing that influences acid strength is bond strength. All right, remember, an acid is something that loses an electron, it loses a proton, a hydrogen ion. So the weaker that hydrogen atom is being held to the molecule, then the easier it is for it to leave. The stronger it's being held to the molecule, the harder it is for it to leave. So the more tightly that a hydrogen is bound, the less likely it is to leave. In this case, HF, all right, it's a fairly weak bond because fluorine is very electronegative. Oh no, I'm drawing this as size. Okay, so fluorine is a very small molecule. And chlorine, now I can't even remember where I was going with this. The bond strength will be determined by the size of the molecules, but it should get smaller. Oh, I see. I'm like, okay. I'm talking about the acid. All right? The acid is getting stronger. Okay? Because in HF, the fluorine atom is very small and tight. And so the hydrogen can get really close to the fluorine. And that shorter length of bond is a stronger bond. Okay? In the chlorine atoms are larger. We're going down the periodic table. And so this hydrogen's actually a little bit further away. It can't quite get as close because that electron cloud is bigger. And so that bond is a little bit weaker. It's sort of a medium strength bond. And then this last one, bromine, we're getting even larger, all right, which is going to mean that that hydrogen's even a little bit further away. So it's the weakest bond. So as the hydrogen's partner gets larger and larger, that bond actually gets weaker and weaker. And the weaker the bond is, the stronger the acid is. The stronger it is going to want to be ripped off of that molecule. And that's where we'll stop for this segment.